Hello, everybody. It is a pleasure for me to chair this session, which is going to be focused on two different topics, which are closely aligned with the strategic lines of the new program of María. So the first speaker, Juan Cuevas, is a very well-known member of IFIMAC. He's a professor in the Department of Theoretical Condensed Matter Physics in the Autonomous University of Madrid. And well, he has been working on several topics in continents areas such as molecular electronics, transferring superconducting structures, spintronics, plasmonics, and many of them. Yeah. So today he's going to talk about a very hot topic, because we are going to talk about heat transfer at the nanoscale. So
I was about to hold my first joke, okay, but I saw okay, so hi everybody, it's a pleasure to be here and give you essentially a bit of a view, essentially how I see the field. To tell you a little bit about, how I see this field essentially and how essentially this fits into the activities of IFIMAC. So I changed the word, essentially the title, and you will understand why in a second. So what we all learn in high school is that heat is essentially the energy transfer essentially due to the difference in a temperature, right? And we all learn that there are three basic essentially like heat transfer mechanism. So if you think about solids, essentially this is mainly dominated by conduction at a microscopic level. This means essentially the transport of both photons and electrons. If you think about essentially how your coffee is getting cold right now is due to convection. Okay, I will not talk much about that. And the other important mechanism is basically radiation, so photons. And since you have very different essentially carriers, essentially this means that it involves many different fields. So again, this is the reason why essentially like heat transfer, in particular the nanoscale, is basically such an interdisciplinary topic. Because at the macro scale, we understand very well essentially the basic mechanism of heat transfer. And the question is, okay, where are the new phenomena, the new opportunities, the new mechanisms at the nanoscale? You have obvious essentially fields like nanoelectronics, nanomechanics, nanophotonics, but you'll see along the talk that there are also some surprises. And now essentially there are fields essentially starting to contribute to this topic. Let me basically organize this in four different essentially like topics. Okay, the first one is maybe the most exotic for some of you, which is radiation. So we all in this room are essentially like emitting thermal radiation because we're at a finite temperature, okay? And everything we know, essentially at least at the textbook level, about thermal radiation is basically described by Planck's law. Famous law that essentially initiated quantum mechanics, okay, and the place is still a fundamental role. Planck's law also established basic limits, okay, for the amount of heat that we can essentially emit in terms of electromagnetic waves and how much we can exchange between bodies, okay? During 70 years, that was the situation, but it was understood essentially that there are certain limits to this basic law. And one of the limits is basically when you bring objects really close together, there is an additional contribution that is mainly due essentially to evanescent waves that was never taken into account essentially in Planck's law. Thanks to that, essentially we can overcome all these Planckian limits, okay, that are closely related essentially to the concept of a black body, okay, and we can do essentially a lot of new physics, and you're going to see some of the opportunities. We actually jumped into this business essentially with the master thesis of Victor Fernandez some years ago. We're teaming up essentially with our collaborators in the University of Michigan, and these are engineers, okay, mechanical engineers. Essentially, we solve the two basic problems. From the experimental side, typically the problem is to align, to bring sufficiently close essentially to objects and to be able essentially to measure essentially the small signal essentially due to this thermal radiation that is driven essentially by a temperature difference. So on the theory side, essentially you have to solve essentially mathematical equations essentially in complex situations, something that is binomial. In this case, actually, what we demonstrated is that basically even a thin film of a few nanometers can emit as much essentially radiation as an infinite body. Okay, and that was the beginning essentially of this field in connection with nanotechnology. Even nanosystems can emit essentially a sizable amount of radiation due to these evanescent waves. Okay. But you see here the scale. Okay, so they managed essentially to bring together essentially these two systems at a distance of 20 nanometers. In nanoscience, we always want more, and more means smaller. Okay, so how to get even essentially to distances of a few nanometers? Okay, with the same colleagues there, essentially is to integrate essentially a nanothermocouple, thermometer for us, okay, in an AFM tip. And this way, essentially, now you can explore this thermal radiation at the scale essentially of gaps of the size of a few nanometers. Okay, and to make a long story short, with the help of Johannes, Victor, and others here in IFIMAC, we essentially established what is still the world record in the sense that we beat Planck's law by 4 orders of magnitude. Okay, so these systems actually emit much more than what is predicted essentially by Planck's law. So what is the field going? Where are the opportunities for everybody working in related things? And this is a topic obviously close to nanophotonics. Okay, so a few years ago, we wrote essentially this paper saying that, okay, now some of the mechanisms are well understood. So now the challenge is basically maybe to move towards applications. The obvious ideas, the most successful one so far is to use essentially these near field thermal radiation essentially to improve the efficiency of solar cells. Okay, this is called thermovoltaics. But many of us have been working on, you know, proposing new kind of thermal devices. Okay, so imagine having essentially the equivalent essentially of diodes, transistors, and so on and so forth, but mediated this time by thermal radiation. Along the way, essentially, there are surprises, okay? Since basically 5 years, we have been applying essentially like artificially intelligent methods, mainly essentially deep learning and also reinforcement learning, actually to try to optimize and improve essentially the knowledge essentially related to radiative heat transfer. Okay, so if you want to know more, Eva will be presenting essentially a beautiful poster this afternoon. Because if I allow essentially to say something about the future of IFIMAC is we shouldn't miss this revolution. Okay, so I don't need to convince you basically that AI is having a tremendous impact in science, right? Okay, so this is the first topic. And you'll see that later is going to be closely connected to the other. When one thinks about essentially thermal conduction, one thinks about essentially the picture you have here. In IFIMAC, the goal has been always like to understand the different phenomena at a smaller and smaller scale. Actually, IFIMAC researchers were basically very much involved in the evolution essentially of electronic devices, at least in the lab framework. Okay, and in that regard, essentially the atomic scale was reached at the beginning of the 90s. And actually, people like Nicolas Agrai, I mean, were absolutely instrumental to use techniques like a scanning tunneling microscope or the so-called break junctions to actually form atomic size contacts, okay, where essentially all the classical laws essentially of electrical conduction simply fail, right? Actually, the field moved forward even to basically be able to bridge a gap essentially by a molecule and try to do essentially what we call molecular electronics, okay, and try to understand if single molecules can operate essentially as electronic components. So I said essentially that we work and partially understood essentially the electronic transport already in the 90s, but it took another 20 years to be at the same level essentially when it comes to heat conduction. Okay, so this was basically the breakthrough a few years ago, in which again with our colleagues in Michigan, essentially for the first time, essentially we discussed and understood the thermal conduction at the level essentially of single atom contacts. And again, where are the challenges there? From the experimental point of view, the challenge is essentially to integrate calorimeters, if you like, essentially in a scanning thermal microscopes, and that would be a challenge that should be taken definitely in IFIMAC. From the theory side, the problem is we know typically a lot about electrons, we don't know so much about phonons. So we have to adapt all our methods, okay, essentially to describe essentially the transport of phonons. And this in principle is supposed to open essentially new avenues, essentially because we have the chance, for instance, in this single junction or single molecule junctions, essentially to study essentially the transport of phonons in new regimes that essentially one cannot realize in microscopic systems. So it took another 2 years, 2019, to basically report the first measurement of the thermal conductance of a single molecule junction, which opened essentially a whole new field. But it came with some problems, okay? Actually, there are 3 groups in the world able to do something like that, but all of them, they seem to find essentially mysterious signals, essentially that almost nobody understands, okay? And this is hindering essentially the field, okay? And basically, this is when IFIMAC people, in particular the group of Nicolas Akraid, essentially has done recently a breakthrough after only 8 years of working on essentially a new kind of thermal probe that has been incorporated into an STM and now allows them essentially to measure the thermal conductance basically at the atomic scale. I don't know if Ruben, are you presenting this afternoon a poster about it? No? Okay. Then, okay, you can ask me questions, okay, but Ruben is going to help. And Ruben also sees essentially these mysterious signals, basically when you have gold contact separated by a few nanometers that we didn't know where they're coming from. And this is basically one of the beautiful things about IFIMAC, that we can have this close collaboration between experiment and theory, okay? So the challenge for us theoreticians is basically to describe in particular the phonon transport essentially in these atomic scale systems, and in particular to develop new methods to take into account effects that are beyond essentially like DFT methods like anharmonic effects and thermal transport. Here the hero is Guillermo, that used to be with us, but he betrayed us and went essentially to the Consejo, okay? And the real heroes are here, Oscar and Pablo, also in the audience there, okay? Where essentially using molecular dynamic simulations, they help us essentially to understand essentially that in particular, in this case, the mysterious signals most likely come essentially from the formation of nanoscale, essentially water mix. Again, many of you saw essentially Oscar talk two weeks ago, okay? Unfortunately, more people are joining. Okay, and now that we understand essentially that this thing, scale, essentially the position of every single atom matters, essentially Pablo in his ERC, congratulations once more, Pablo. Okay, is taking the challenge essentially to use in particular essentially what is called deep enhancement Raman scattering to actually look at the impact of single defects essentially in the thermal transport. Okay, so if you have more questions, Pablo is the guy. But something that I like to emphasize is it's not all about essentially how the heat is being conducted, but it's also about how you manage the heat in all these nanoscale systems and how the heat is being dissipated. So this brings me to what is called Joule heating that we all learn in high school, and we all know that when you drive a current through essentially a wire, there is basically heat being released, okay, and it depends on the resistance of the wire. But again, things get really interesting when you go to the atomic scale, because often most of these systems have dimensions that are much smaller than the inelastic scattering length for all the carriers, meaning essentially that electrons, okay, and phonons go through these systems ballistically, okay, without dissipating essentially energy. So what is the energy being dissipated, okay? So for the first time, essentially, we have the source of resistance and the dissipation occurring in 2 different places, okay? And this is basically a challenge we took. Essentially, the driving force was Linda, essentially like 10 years ago. But again, with our colleague in Michigan, essentially, we understood essentially what is the determining factor essentially in this case. Okay, again, from the experimental side, the analysis of the Joule heating in these atomic scale systems was possible essentially thanks to the use of these modified scanning tunneling probes that you see here that they incorporate. Essentially, you see 2 metals touching. This is a thermocouple. This is a thermometer that is measuring essentially quite locally, essentially the dissipation that is taking place. And from the theoretical point of view, we understood essentially that it's all about essentially the transmission, the probabilities for electrons essentially to go through this system, something that we can tune by tuning, for instance, the molecular architecture. So again, now IFIMAC researchers, Julio and Pablo and his students basically are taking the challenge essentially to look at Joule heating at the nanoscale using essentially the experts in AFM and related techniques, essentially like this 2 omega method. Essentially, what you see here is a gold nanowire, and this is being probed essentially by an FM technique, okay, by FM tip, and what you're looking is basically the local heating, if you want, okay, that is taking place. The thermal expansion essentially of the FM tip that you can hopefully translate into a local temperature, okay? And the opportunities are amazing, and Pablo was telling me about essentially what you're doing with these viruses, and I think you should give us essentially a seminar soon, because I would love essentially to hear more about this stuff. But you get surprises, okay? Often essentially like Joule heating sounds like, okay, this is something negative that I try to avoid, but people like Eduardo Lee is actually using this essentially in a constructive manner, and essentially in this case, in the context of these superconducting circuits, where you see these nanowires that are both semiconducting and superconducting, okay, and in these circuits, the analysis of the Joule heating actually give you some new insight into the transport properties of these essentially, superconducting circuits. And actually, he's going ahead and using essentially the Joule heating to actually develop new low temperature thermometers and bolometers. And bolometers means very sensitive detectors of microwave radiation. And the last topic that I want to briefly mention is you see there is a close connection between essentially heat conduction and essentially electricity. And this is what we teach basically in solid state physics, okay? Enrique and I, we're teaching this these days. Essentially, these are the so-called essentially thermoelectric phenomena. One example. This is the so-called Peltier effect, and it's called like that because Peltier discovered back in the early, essentially 19th century, that if you drive an electrical current essentially through a junction, you generate essentially a heat current. Okay? And by this means, essentially what you can do is, for instance, to heat up one of the electrons by cooling down the other one. And that's the reason why essentially this phenomenon is the basis of these thermoelectric coolers, essentially, that have many different applications in electronics. Okay? When I was a kid, essentially, we used to go essentially to the countryside. Well, I was living in the countryside. We were taking excursions and taking essentially this fridge with us. Okay? This has one of these electrical fridges, if you like. Okay? But again, when you go all the way down essentially to these atomic scale circuits, the question is, what are the mechanisms? Okay, so can you still use essentially these circuits actually to have Peltier cooling, okay, and use essentially these systems as electronic refrigerators? And the answer is yes. And again, this is something we tackled some time ago, essentially again with Linda as the driving force, where again with our same colleagues, essentially we understood essentially that you can use single molecules and design single molecules to actually operate as thermoelectric coolers. Okay, and now the goal as usual is like how to optimize this kind of phenomenon. Okay, and actually thermoelectricity has become a big topic essentially in everything we do, because we have learned essentially that by measuring thermoelectricity in particular, essentially what is called the thermal power, in this case the connection between a temperature gradient and a thermal voltage, okay, you can learn a lot about all these nanoscale systems. And actually, I mean, here the key person has been essentially Nicolas Agrayo, which is basically the worldwide expert in the measurement essentially of thermal power in these atomic and molecular systems. Okay? And actually, he has spent the last 15 years, essentially, he has, told me that he has probably 30 papers about measuring thermoelectricity actually in these single molecule junctions, because essentially they provide additional information that is not really contained, for instance, in the electrical current. Okay. So in this context, okay, there are many more people essentially joining, in particular, a lot essentially with Rafa Sanchez is doing, okay, in the context of these nanoscale systems and quantum transport, seen essentially and investigating where the new opportunities actually for thermoelectricity in these kind of systems. Okay, and actually this is only part of the larger activities that are also related, I would say, essentially with thermal and heat transfer. Okay, which is becoming a big deal these days. That is to the study of quantum heat engines, and more generally, essentially what is called quantum thermodynamics these days, and the connection actually with quantum transport both charge and heat. Okay, so he's obviously one of the leading persons basically in this talk. Okay, so I want to close this by simply essentially repeating maybe the main message of this talk, that is heat conduction and heat transfer is probably the last unexplored frontier or territory, if you like, essentially nanoscience. You have seen that we're making progress, but still, believe me, there are many open challenges. And actually, IFIMAC is perfectly suited essentially to keep contributing essentially to this field, because as you have seen, essentially there are many different aspects essentially that requires many different expertises that only a place like this can have. Okay. So as Pablo said, essentially in his ERC, let's let the heat flow. Okay. So thank you very much for your attention.
Thank you very much. Thank you. Well, thank you very much for the interesting and comprehensive view on heat transfer. I'm sure there are many questions. Question? I think it's exciting.
It's like my classes, okay? Nobody has any question because I'm so clear, right, Thomas?
I have a question.
You can confirm this, right, Thomas?
I have a question. So many things. Could you comment a bit more on these thermal photovoltaic devices?
Yeah, this is one of the most beautiful things. Actually, I mean, well, I will not tell you the entire story, but I was about to leave Spain essentially to create a company essentially on this topic. So I think I never told the story, but anyway, so what is the point here? The point is our sun is stupid. And it's basically, you know, we get essentially the energy from the sun and it's thermal radiation. But it's a broad band. It's actually an excellent black body, and it's described essentially by Planck's law. Okay, so we need a more clever sun. So the basic idea of coming essentially from near field thermal radiation is the following: what if we replace the sun by something that emits more intelligence? And there are two aspects here. One is if I bring it sufficiently close essentially to a PV cell, I'm gonna essentially like inject more power. Okay, so I'm gonna generate more electricity. The other thing is that by tuning essentially like your material, by doing kind of metamaterial physics, okay, you can actually engineer the spectrum. An idea is essentially if I take, I don't know, if I emit monochromatically out the energy of, for instance, the silicon solar cells, I'm gonna reach the theoretical essentially like limit essentially predicted by software. Not only reach, but actually overcome. Okay, because I can emit more and more clever. And there are a lot of people essentially working on that already. The problem is the idea works, but it's still too expensive. So it's not clear essentially that you're going to see soon essentially like the standard solar cells replaced essentially by this kind of near field devices. And the challenge is, remember, I told you you have to bring these two things and align them perfectly essentially in a scale definitely below essentially 1 micron. That's challenging and definitely really expensive so far. But who knows? Okay, so.
Yeah. Thank you. Yes,
Yeah, next talk. My question concerns thermoelectricity. You mentioned at the end of your talk. Well, as you know, thermoelectricity is now a hot topic or a topic relevance related to the energy crisis. A lot of heat is dissipated by many human devices, and a lot of people are trying to make use of this heat. And one way of using this dissipated heat is thermoelectricity. What brings new thermoelectricity at the nanoscale compared to what we know now in past thermoelectricity? What could we expect? You know already what we can expect.
This is one of the main topics. The basic idea, essentially, I mean, if you want to characterize any device, an electronic device, essentially in terms of thermal electricity or quantum engine, heat engine, I mean, there's a number which is called the figure of merit. It involves essentially, among other things, the thermal power. Okay, it involves also essentially the thermal conductance. It's all about essentially improving the the thermal power, okay, without increasing too much, at least the thermal conductance, okay. So one of the key ideas, for instance, here is that in our case, the thermal power is simply determined by the slope of the transmission of the Fermi energy. So make the slope as big as possible. One idea is use quantum interferences. Then you can have a final resonance, maybe that has almost an infinite slope. So I can get essentially the highest thermoelectric power ever. Okay, so even if I compare this with microscopic systems. Actually, because a guy had essentially like for 4 or 5 years an entire European project essentially pursuing this idea, they failed. But still the idea in principle theoretically should work. Okay, it's just to find essentially the right molecule, essentially that does something like that. So there are opportunities essentially to boost the thermal power essentially using this and using essentially like the coherent transport mechanism that you have on nanoscale. Okay.
Yes.
Yeah.
So I'm going to anticipate something we will hear about later. So this is clearly a topic that is really strong in IFIMAC and it's related to Luisa's question. Have you thought or do you have any plans to promote this into the direction of knowledge transfer? Because we know, at least from the first part, which is the one that I know the best, that there are industrial avenues already open by all this relative cooling and all that. Do you see opportunities for IFIMAC in this direction?
One of the things that, for instance, Juan was working on essentially during his thesis was what is called passive radiative cooling. Probably you know what this is. I put an object, essentially I expose it to the sunlight and it gets cold without electricity, without power. And sounds like magic, right? But actually we have different ideas of, and we use essentially these neural networks to actually optimize these devices, okay? And we actually contemplated the possibility actually to find a patent, but when you talk to people, again, most of the realizations we come out with are expensive. We're very good at essentially basic science, but when it comes to actual realization of these devices, it's still not good enough, our fault, okay? But this is one of the ways to go. The other way, essentially, that actually, I mean, my colleagues, essentially, you know the story, I mean, they actually have several patents on these, essentially, like near-field thermal photovoltaics. And at the end, essentially, for people like us, essentially also working on nanophotonics, is about essentially improving, essentially, in this case, the emitter. And you can use essentially all the tricks you know, essentially, I mean, from nanophotonics. Okay, you have to translate this from the visible to the infrared because we're talking about thermal radiation, but many of the concepts applied immediately. So it's all about essentially finding the right metal material, the right metal surface, actually to boosting actually the efficiency of the PV cell. So there's no question that. And as I mentioned, we're also working on that. Okay, I think the challenge now is to bring this to final technology. Okay, and we're definitely committed with that. We have nothing clever enough so far. Okay?
Last question.
Thank you very much for this excellent talk. I took some pictures for my students.
You can get the slides.
Okay, thank you. So I just wanted to mention that there is a new activity in IFIMAC. We published only last year the first publication in Europe. It's basically a continuation, experimental continuation of what Sebastian Bergeret predicted like 20 years ago, is very high thermoelectric power in between superconductor and exchange by in exchange field, so it's a big superconductor and ferromagnet. So we are continuing this, and there are big predicted high efficiency thermoelectric generators in this area, and we are actively working on this. Just let you know probably for you.
No, thank you.
It's important to mention.
I include this, okay? That's part of the problem, okay? So actually the mechanism is exactly the same. It's about increase essentially the slope of the
yeah, but it will be working probably for quantum computers in the future because it works mostly for critical temperature. temperature.
Yeah, most of the
Different
time,
temperatures, sorry.
all these experiments are room temperature. Obviously, you're talking about private temperature.
Okay.
Thank you. Ready to have a time to very short question and very short answer.
Okay, I'll make the question, because I think that the answer will not be short, and then we can discuss during coffee break. I think this is difficult, but you have to say what is the main bottleneck in the theory and experiment in the field. Could you identify that? Maybe what is missing in our theoretical description of this object, and what is the bottleneck from the experimental point of view as well?
Very quickly, when it comes to thermal conduction, essentially, like from the experimental point of view, is to improve the sensitivity of these thermal probes. Clearly, because if you want to discuss essentially what happens in a molecule, you have to go in some cases on the order of picowatts per Kelvin at room temperature. Yeah. Okay. From the theory side, we're actually tackling this with PEM, which is so far our methods basically were not included all the phenomenal effects that you see essentially in phonon transfer, which are inelastic scattering, and also the thing that is, I don't know if you can see it here, but this is how a molecular junction looks like at room temperature. And this is what we mean essentially when we do DFT, thermal fluctuations, stability, and things like that. So we're actually working on these two fronts, and Juven is going to continue working, improving essentially the sensitivity with the help of Pablo, again, and Julio. So these are the two main challenges. Unfortunately, I mean, we're actually already working on them.
Well, thank you very much. Let's thank Juan Carlos.